Have you ever noticed how some objects seem to leap toward a magnet while others sit completely unaffected? That fascinating difference lies in the magnetic properties of materials. At the atomic level, every material contains electrons that spin and orbit around the nucleus. These motions create tiny magnetic dipoles, little atomic magnets. But whether a material responds to an external magnetic field depends on how these dipoles behave collectively. We classify materials into three major types: diamagnetic, paramagnetic, and ferromagnetic. Let's start with diamagnetic materials such as copper and bismuth. These materials actually get repelled by magnetic fields. Why? Because they develop a weak magnetic moment opposite to the applied field. Their magnetic susceptibility, denoted by Chi, is slightly negative. Next are paramagnetic materials like aluminum and platinum. These have unpaired electrons that naturally create permanent dipoles. When placed in a magnetic field, these dipoles tend to align with the field, giving a weak attraction. That's why their susceptibility is small but positive. And finally, the stars of the show, ferromagnetic materials such as iron, cobalt, and nickel. In these materials, atomic dipoles strongly align in the same direction, even without an external field. This cooperative alignment produces an intense attraction, which is why iron filings jump so dramatically toward a magnet. To picture this, imagine placing the three types in a magnetic field. Diamagnetic materials will gently drift away, paramagnetic ones will slide slowly toward the magnet, while ferromagnetic materials will snap right to it with great force. So, to sum up, the way atomic dipoles align or resist aligning explains why different materials show different magnetic behaviors. Diamagnetism repels, paramagnetism weakly attracts, and ferromagnetism creates powerful magnets that we rely on in motors, transformers, and everyday devices. Have you ever wondered why some materials are slightly repelled by a magnet while others are faintly attracted? This difference lies in the contrasting behaviors of diamagnetism and paramagnetism. Diamagnetism originates from the motion of electrons in their orbits. When an external magnetic field is applied, it induces tiny changes in this orbital motion, which in turn produce an opposing field. That's why diamagnetic materials always show a weak repulsion. Paramagnetism, on the other hand, comes from permanent magnetic dipoles of unpaired electrons. These dipoles naturally tend to align with the applied magnetic field, leading to a weak attraction. Now let's talk about the effect of temperature. Paramagnetic behavior weakens as temperature rises because thermal agitation disturbs the alignment of dipoles. Diamagnetism, however, remains unaffected by temperature changes. This difference gives rise to a key susceptibility trend. Diamagnetic susceptibility, represented by Chi, is independent of temperature, while paramagnetic susceptibility decreases with temperature, following Curie's law. Mathematically, Chi equals C divided by T, where C is a material constant and T is the absolute temperature. So, to sum up, diamagnetism is always weak and negative, opposing the field, while paramagnetism is weak and positive, aligning with the field but diminishing as temperature increases. Together, they highlight how the microscopic nature of atoms shapes the magnetic properties we observe in real life. Have you ever wondered why iron sticks so strongly to a magnet while aluminium barely responds? The answer lies in a special class of substances called ferromagnetic materials. The defining characteristic of ferromagnets is that they can exhibit magnetization even without an external magnetic field. This happens because of the strong internal alignment of atomic dipoles. In other words, the atoms act like tiny bar magnets that naturally lock into the same direction. Now, let's understand this using the concept of magnetic domains. Imagine the material divided into small regions where all dipoles in each region are perfectly aligned. Without an external field, these domains are randomly oriented, cancelling each other. But when a magnetic field is applied, the domains reorient and grow, resulting in a strong net magnetization. One fascinating property of ferromagnets is magnetic hysteresis. This means that even after the external field is removed, the material retains some magnetization. That's why permanent magnets exist. Their domains stay aligned long after the magnetizing influence is gone. As an example, iron is one of the most common ferromagnetic substances. It has a Curie temperature of about 1043 Kelvin. Beyond this temperature, thermal agitation overcomes the alignment and the material loses its ferromagnetic nature. So to summarize, ferromagnetic materials are unique because they show spontaneous magnetization, domain alignment under fields, and hysteresis. These very properties make them the backbone of technologies ranging from electric motors to data storage devices.
Have you ever wondered why some magnets stay magnetized even after you stop applying a magnetic field, while others quickly lose their magnetism? The secret lies in a fascinating phenomenon called magnetic hysteresis. By definition, hysteresis is the lag between the magnetization of a material and the applied magnetic field when it goes through cycles of magnetization. This lag is captured beautifully in what we call the hysteresis loop. If you look at the graph on the slide, magnetization is plotted against magnetic field intensity. The resulting loop tells us not only how the material responds, but also the energy lost as heat during each cycle, represented by the area enclosed within the loop. Now, two important terms emerge from this curve. First, remanence. This is the magnetization that remains in a material even after the external field is removed. It's the very reason permanent magnets can retain strength over time. Second, coercivity. This refers to the reverse magnetic field intensity required to reduce the magnetization back to zero. Materials with high coercivity make excellent permanent magnets, while those with low coercivity are better for temporary or soft magnetic applications like transformer cores. So to summarize, the hysteresis curve tells us not just about magnetization, but also about energy loss, remanence, and coercivity. These insights guide us in choosing the right magnetic materials, whether for storing data, building motors, or designing transformers. Have you ever wondered why the magnets in a transformer are not the same as those in a refrigerator door or a loudspeaker? The secret lies in the difference between soft and hard magnetic materials. Let's explore this fascinating distinction. Soft magnetic materials are those that can be magnetized and demagnetized very easily. They have a narrow hysteresis loop, which means they respond quickly to changing magnetic fields. Because of this property, soft materials like soft iron are used in devices such as transformers and electromagnets, where the magnetic field needs to change rapidly. On the other hand, hard magnetic materials behave quite differently. They retain magnetization once magnetized, and that's why they have a wide hysteresis loop. This makes them perfect for permanent magnets. Materials like steel or alnico alloys are classic examples. Now let's talk about energy loss. Since the hysteresis loop of soft materials is smaller, they lose less energy per cycle, which makes them efficient for alternating current applications. Hard materials, however, have larger energy losses, but provide the stability required for permanent magnet design. To summarize, the choice between soft and hard magnetic materials depends on the application. If you need dynamic magnetic fields, like in transformers, you go for soft materials. But if you need a strong, stable, and long-lasting magnetic effect, as in permanent magnets, hard materials are the obvious choice. So, the next time you see a transformer buzzing or a fridge magnet holding a note, remember, it's the material's magnetic nature that defines its role. Have you ever wondered why certain magnetic materials lose their magnetism as temperature rises? This curious effect is beautifully explained by Curie's law. Let's explore with an example. Suppose we have a paramagnetic material whose Curie constant is 1.2 Kelvin, and we need to find its susceptibility at a temperature of 300 Kelvin. Step 1. We recall Curie's law, which states that susceptibility, denoted by chi, equals C divided by T. Step 2. Substituting the values, we put C equals 1.2 and T equals 300. So chi equals 1.2 divided by 300. Step 3. Calculating this gives chi equals 0.004. This small value tells us that the material's magnetic susceptibility decreases significantly with rising temperature. In fact, higher temperature introduces random thermal motion that disrupts the alignment of atomic dipoles, reducing the net magnetization. So to sum up, Curie's law shows us that magnetism and temperature are closely linked. The hotter the material, the weaker its alignment with an external magnetic field. I hope you now have a clearer picture of how Curie's law governs the magnetic behavior of materials. In our next session, we'll uncover more fascinating insights into the world of magnetism.
Let's take a moment to bring everything together. Magnetic materials come in three major categories: diamagnetic, paramagnetic, and ferromagnetic. Each of these responds to external magnetic fields in its own unique way. Their behavior is largely defined by key properties such as magnetic susceptibility, remanence, and coercivity. These determine whether a material weakly opposes, weakly supports, or strongly sustains magnetization. Now, temperature plays a crucial role too. For both paramagnetic and ferromagnetic materials, heating tends to disrupt atomic alignment, reducing their magnetic response. This is why the Curie temperature is such a critical threshold. When it comes to applications, soft magnetic materials like soft iron are used in coils and inductors where rapid switching is needed, while hard magnetic materials such as steel or alnico are used to create permanent magnets. And finally, here's the exciting real-life impact. From MRI machines that scan the human body to electric motors that power our vehicles and appliances, magnetic materials are at the very heart of modern technology. So to sum up, understanding magnetic properties is not just about theory, it's about seeing how these principles shape the devices and tools we rely on every single day.